Okay. Oh man. Some more work. The Pokemon Kaggle analysis. All right. I am gonna do something that's a little bit different. I went to a meetup on Friday, and I explained to them this Pokemon Kaggle dataset. Like, it was just me and this one other guy, and he's actually really cool. The thing is, like, he asked really important questions. So, like, you know how we're using logistic regression to actually predict the probability of whether if the first Pokemon won that battle or not? And he asked a very crucial question where he said something in the lines of, I wrote it down, I forgot what it was though. Oh, you know what, I'll be right back. I think it's in my other thing. So I went to that meetup, and he asked a really good question. Let me think. So how does each data point assign a value, and how does it calculate the probability of the answer? Well, so I've done a bit of a digging regarding logistic regression. This should be like, I should know this before I even start doing it, but I only know that logistic regression only just calculates the probability of a dichotomous prediction outcome of whether, most likely, whether if A is better than B, or A, like if it's preferred A or B or something like that. So let's see here. So to answer that question, this is like for my sake too, but really, like, how logistic regression goes is that you have like a plane, right? And then you have all these data inputs, and then you have this thing called the linear boundary line, where it tries to find, like, it tries to find the separation between the two dichotomous outputs, A and B. And in order for them to do that is that the points will always either be one or the other, or actually on the line, which is a 0.5, exactly 0.5 of the logs function. But other than that, the reason why they do that is because it try to calculates like the boundary function. And how that happens is that there is this thing called the log odds. So what you do is that you actually try to find the odds ratio. You find the probability of whether if the probability of that one data point, if it falls on the positive side, which means like either if it's true or false, you know, let's say it's true, right? If the answer is true or false, it tries to find the probability of where it lies on true divided by 1 over 1 minus true, which is the false. That's just an example. It would be like positive or negative. But then that probability only just tries to go from 0 to infinity. Let me see. I'm confusing you guys, fuck, because I just don't know myself that very well. I got it, I read it, and I was like, oh, okay, that makes sense, but now that I'm trying to replay it, it's like, it doesn't make sense. I'm thinking things very, very complicated. P of x divided by 1 over 1 minus P of x. The probability odds convey the exact same information. Our boundary function gives a value from negative infinity to infinity. So what we do is take the logarithm of the log odds function that goes from 0 to infinity. But then if you log it, log of the odds ratio of x goes from negative infinity to infinity. So the boundary function actually defines the log odds of the plus class in our model. So essentially in our two-dimensional example, we give an AB. This is what the logic regression should do. Compute the boundary function, compute the odds ratio, and then knowing odds ratio, it would compute P plus using simple mathematical relations. What in the world, Alec? So I think, like what I said before, like ultimately in a high level view, logistic regression really just tries to calculate the probability of whether if it's true. So in this case for Pokemon, whether if the first Pokemon actually won or not, and it tries to calculate the probability of that. How it does that, let me re-summarize again. Let me really rephrase this again. I'm gonna use my tablet. I'm gonna follow along with this thing just to really like get a grasp on it. I only read it, but I didn't really like thoroughly studied it or even like put that into my heart. Let me use this. I make this bigger? Is it this? Okay, well this is good enough. One sec. Sorry about that. I had to do something before I start. So log regression. Let me tell you what I know. Right now, what I know is that log regression is very useful finding the probability of whether something is true. Or whether if something is true or positive or anything like that. So if the dependent variable consists of 0 and 1s, you know, like if we had like all this like data points and then the outcome has 0 and 1s, it would try to find the probability whether, but then it has all these other like predictors called all these predictors. It tries to calculate whether if it falls into the line of whether if it's true or not, or the probability of whether if it's true or not. Now this is where I need to really find out, okay, how does that work? Well, this is where I try to like study it like right now. Like, first of all, like the central assumption of logistic regression is whether the input space is separated into regions. For each class, one for each class. By a linear boundary. So then in the article it says, what does linear boundary mean? For 2 dimensions, it's straight line, no curving. So it kind of looks like this. For 3 dimensions, it could be a plane. This boundary will of course be decided by your input data and the learning algorithm. It is clear that the data points must be separable into 2 aforementioned regions by a linear boundary. If your data points do satisfy this condition, they are said to be linear separable. So this is really important. If your data points satisfy this constraint, they said to be linear separable. If it satisfies the data points like that. So the dividing plane is called a linear discriminant. Oh, that's kind of interesting. I just now noticed that you could do LDA, which is linear discriminant analysis, by really understanding whether if the linear discriminant is actually really right. But I learned that in school, and I should really get back into that. It's linear in terms of function. So the dividing plane, called linear discriminant, it's linear in terms of its function. It helps the model discriminate between points to different classes. Now, can I say this without even looking at this shit yet? No, not yet. Points aren't nearly separable in the original concept. You could consider, how does that work? But how does log regression use linear boundary to quantify the probability of a data point belonging to a certain class? So So how does log regression calculates the linear boundary, basically? Okay, so this is where I kind of need to really figure this shit out. So how does the log regression calculate the boundary to quantify the probability of a data point belonging to a certain class? So if we have two input variables, let's say like HP and attack percentage using the Pokemon, and then as well as the coefficient. We always need the coefficient for some reason. So B of O plus B1 X1 plus B2 X2. This could be HP. This is the coefficient, and this could be the attack right here. This X. Now let's say like if the coefficient is like what, I don't know. Let's not worry about the coefficient because I really don't know. But if it's like 43 plus 72, and this is attack, and this is HP. So there's three things to consider. These two actually lies in the division of the plus class. So let's say this is the plus class right here, and this is the minus class. So this thing right here, this thing could either be here, or even on the line, which is a 0.5. That's what it's basically saying. It's not really calculating how exactly it calculates the probability, but it just tells us like it calculates the probability that it's on the plus or the minus. This part is kind of confusing, but I think I know what they mean. This whole plane right here is an infinite space, and each row of data, it tries to calculate the probability of whether this is good or bad. But then since this plane is an infinite thing, this is bad, hold on a sec. We kind of want to actually have to convert it to from 0 to 1, but right now this is from infinite, negative infinity to infinity. Let P of X denote the probability of X occurring. But now we have to map this probability that goes from 0 to 1. How do we do that? It has to be 0 to 1. So then now we have to use this thing called the odds function. The odds function is basically, in that case, P of X over 1 minus P of X. P of X representing this thing, like this example, and then whether if it went on the plus side, and then 1 minus P of X is basically this same thing, but then it landed on Well, anyways, no, never mind. Let me take a step back. Let me take a step. I'm still confused with this a little bit. I apologize. But what we do need to do is that huh. How do I do this? Oh my god. Sorry about that. I'm so confused sometimes. So where am I? Uses the probability P of x over 1 minus P of x. This is the odds function, basically. And this is essentially like how logarithmic regression calculates. It doesn't really tell you exactly how this works, so let me look at a different source. I don't think you can really like translate this, but it just means that it's the log odds where P of x represents the probability that the point will take on a response value of 1. So like this is like I just said in the very beginning, like what's the chances of having that first Pokemon win? That's basically what the log regression does. That means that the estimated probability based on the values of predictors takes on the form shown here. That's all it just keeps saying. I'll be right back. Oh man. Let me check something else on looking at the book.
Appreciate the sentiment, but I'm afraid it's nothing more than a daydream.
Oh. Okay, this one actually makes a little bit more sense. We must model a p of x using a function that gives outputs between 0 and 1. Yeah, I remember, I just said that. We use the log regression, or we use the log function. So the probability of x is e to the b0 plus b1 of x over 1 plus e to the b0 plus b1 x. Whoops, sorry, that's an x. To fit the model, we use a method called maximum likelihood. There's a method called maximum likelihood. which discusses in the next section. The right-hand panel illustrates the fit of the log regression model to the default data. Notice that low balance is an okay, blah, blah, blah. Likewise, for high balance, we predict the problem. So basically, like I said before, it just keeps saying the probability of finding whether if the first Pokemon wins. The log function will always produce an S-shaped curve. Anyways. Man, my handwriting sucks. So like P of X. So after let's see here. And so regardless of the value, we will obtain a sensible prediction. We also see that the log model is better able to capture the range of probabilities that is the linear regression model in the left-hand plot. Okay, yeah. The average fitted probability in both cases is 0.0333, which is the same as the overall proportion of whatever. So using this thing right here, and then we manipulate it by saying P of X over 1 minus P of X. And then after that is called this is called the odds ratio, which we've read in that other thing. And this takes on the value zero to infinity, right? Indicated very low, which indicates very low and very high probabilities of the default respectively. For example, on average, 1 in 5 people, the odds of 1/4 will default. 0.2 implies that. Okay, so good. This is an example right here. So for example, I'm going to use this blue. So 1 in 5 people, a quarter, whoops, that's not a quarter. Has, whoops, oh my god, bro. Okay, so a quarter would, like, 1/4 is probably like a quarter of, there's a high probability that a quarter will default out of the confused is that what is the odds? So it'll say the values of odds close to 0. Okay, I actually have a PDF version of this. So right here, like so this is what it is. It'll just be exactly like this. This will turn into this to find the odds between negative infinity and infinity. But then once we find the odds, it'll just turn to 0 to infinity for some reason. The quantity of p of x over 1 minus p is called the odds, and can take on any value between 0 and infinity. The values of the odds close to 0 and infinity indicate a very low and very high probabilities of whether if the Pokemon turn into 1, respectively. For example, on average, 1 in 5 people with the odds of a quarter will default, since p of x equals 2.2 implies an odds of 0.2 over 1 minus 0.2 equals a quarter. Likewise, on average, 9 out of 10 people with the odds of 9 will default. Since p of x equals 0.9 implies odds of 0.9 over 1 minus 0.9 equals 9. Odds are traditionally used instead of probabilities in horse racing, since they relate more naturally to correct betting strategy. By taking the logarithm of both sides, we arrive at b over b of x. How come this doesn't like get any bigger? How come I can like zoom in this one, but I can't zoom in this one? Oh man, it won't let me zoom in. Oh well. Let me see what this guy says. Understand log regression model function, definition word by word. It uses a black box function to understand the relation between the dependent variable and independent variables. No, that is way too generic. That's like saying an apple is a fruit. Fuck yeah. Yes, I know what independent and independent variable is. So likelihood just basically means that what's the probability of this person will do something. This is kind of easy to understand maybe, but it's way too generic. So we have all these things, and then I guess this part is the log regression. It's a black box model. It's whether if it's happy or sad. Why is everything black box? That's the problem. I just don't get it. Okay, so we have penguin activity description, and this is probably the dependent variable, whether it's happy or sad. Yeah, I get it. Has all these activity scores, weights. This doesn't really explain it either. That's interesting. I think this is the best one, and it still doesn't really tell you. I mean, it's the best one, but it still doesn't really tell you how it calculates mathematically. But I guess, I just have to figure out the hard way because there's no other good sources. I get it, but how does it exactly work? Discussing a non-statistician colleague, it seems that the log regression is not intuitive. Some basic code. Why don't use the linear model? What's logistic regression function? How can we compute hand step-by-step to listen to what is dealing with the GLM function? Okay, that's good. Oh my god, this makes so much sense. Oh wow. They used gradient descent to do that.
Let me talk about logistic regression model building using SAS. Logistic regression models are also called logistic regression model building is also called grade scoring. So I'm going to talk what it is, and I'm going to talk what are the steps of model building. So what is logistic regression model building? Let's take a scenario. Scenario is that you have set of accounts which are open between January 12 to March 12, and you have lot of their behavior as of account opening date. So for example, number of times delinquent in past 12 months with other banks. So it is roughly January 11 to December 11 performance for the account which are open in January 12. For the account which are open in March 12, it will be April, it will be actually March 11
Where
to
in the
February
world is this shit?
12 performance. So you have total outstanding on loan products at the time of account opening, maximum utilization in past 12 months at the time of account opening. So you have a lot of behaviors, and you have after 24 months you are taking a look how many of them actually became defaulter, which are shown as red, and how many of them are actually good. So you have these independent variables, and this is the dependent variable. Dependent variable is actually binary 0 1, and these are a lot of independent variables. Now what is logistic regression modeling? In reality, it is all about you are selecting best 5 to 15 independent variable from the list of huge number of variables, and then you are developing an equation like this, where you are taking log probability of 1 divided by 1 minus probability of 1 means like probability of 0. So it's actually odds log probability of 1 by probability of 0. You are taking log probability of 1 divided by 1 minus probability of 1 means like probability of 0. So it's actually odds log probability of 1 by probability of 0. Then here you have intercept, and here xy is independent variable and bi is the coefficient of independent variable. So you have, if you have taken n independent variable, that's how it will come, and ultimately you will develop an equation like this, where it is essentially you are calculating probability of 1. Now at the time of account of 4 month modeling, in reality it is all about you are selecting based 5 to 15 independent variable from the list of huge number of variables, and then you are developing an equation like this where you are taking log probability of 1 divided by 1 minus probability of 1 means like probability of 0. So it's actually odds log probability of 1 by probability of 0. Then here you have intercept, and here xy is independent variable and bi is the coefficient of independent variable. So you have, if you have taken n independent variable, that's how it will come, dependent variable and b0. Then here you have intercept, and here xy is independent variable and bi is the coefficient of independent variable. So you have, if you have taken n independent variable, that's how it will come, and ultimately you will develop an equation like this where it is essentially you are calculating probability of 1. Now it looks very simple, but if you go in next step and you think of how you have decided 24-month itself, that will require you to do something like vintage analysis. Vintage analysis actually goes through, and what it does, it actually takes all the accounts which are open, and then it sees how its performance after 3 months, after 6 months, after 9 months. And if you see what it has done, it has taken accounts open in Q4 2010, Q2 2011, Q4 2011, Q4 2012, and seen how they have behaved after 3 months, 6 months, 9 months, 12 months. And based on that, you decide that okay, you'll be going 24 months, 27 months, 18 months, and all those things. The idea is that you will select the short duration which captures the performance till it becomes stable. Next, how do you select 5 to 15 variables? This itself is a process, and for this process what you do, the first step is actually you have to get a feel of the data. How do you get a feel of the data? Like the very way the doctor gets a feel of the patient, as a modeler you need to get a feel of the data. And there are a lot of statistical procedure like contents, proc print, proc frac, proc univariate, which actually gives you a lot of output. What you need to understand, the SAS procedure in itself are huge amount of automation. They produces lot of statistics. For example, if you talk of proc univariate, in this whole thing
He lost me here.
Feel of the data. Q2 2011,
He lost me until here.
Q4 2011, Q4 2012, and seen how they have behaved after 3 months, 6 months, 9 months, 12 months.
This is
And based on that, you
vintage
decide
analysis. What the hell
that
is
okay,
this?
you'll be going 24.
I have no
do
idea what
something
vintage
like
analysis
vintage
does.
analysis. Vintage as a modeler, you need to get a feel of the data.
Yeah,
There are a
that's
lot
right.
of statistical
I mean, that's like the
procedure
general rule.
like contents, proc print, proc frac, proc univariate, which actually gives you a lot of output. But
Okay,
central
okay, I get what he's
tendency,
saying now.
why are
It's
you getting
just
plus sign here?
all he's doing
What
is
is
just.
the meaning of next
So
step?
basically, you just
It
EDA
shows that
is what he's
Fisher's
saying.
linear discriminant function. So these are the things, some of the things that is required. Course on Udemy on all those things. The course outline you can take it.
I don't know. He's just talking about generic shit. Everyone just keeps saying that. Logistic regression uses log p over 1 over p, 1 minus p. So I have many questions still. Like if I'm going way deeper into the rabbit hole, why can't I grasp the situation? So they're just telling me, okay, to determine whether if one's an orange and you have to find the maximum likelihood of the orange. And the maximum likelihood of the orange regresses on this log odds called p of x over 1 minus p of x logged. And that's all they ever talk about. That's basically how it is. I don't know why. Why is it log odds? Is like, what's the math behind that. What's the illustration? Like, how do you put the all the data points into it? Oh, yeah. Why can't I digest this? Consider a point AB, plugging the values of x1 and x2 into the boundary function. We will get the output b of 1a and b of 1b. Okay. Now, depending on the location of b, a, b, there are three possibilities: above, below, and on the line, on the linear boundary. Great. So now we have a function that outputs negative infinity to infinity, giving an input data point. But how do we map this to the probability? Okay. So now we just need to map this to the probability. And the answer is in the odds function. This makes so much sense, actually. My mind is just cluttered right now. So this is defined, which is essentially the ratio of the probability of the event happening versus not happening. Okay. It is clear that probability and odds convey the exact same info. But as p of x goes from 0 to 1, odds ratio goes from 0 to infinity. Or we just look what it is. Since our boundary function gives a value from negative infinity to infinity, is take the logarithm of odds ratio, called the log odds function. Mathematically, odds ratio goes from 0 to infinity. Logarithm goes from negative infinity to infinity. So we finally have a way to interpret the result of plugging in the attributes of an input into the boundary function. The boundary function actually defines, okay, so we finally have a way to interpret the result of plugging in the attributes of an input into the boundary function. The boundary function actually defines the log odds of the plus class in our model. So we finally have a way to interpret the results of plugging in the attributes of an input into the boundary function. Keep forgetting what boundary function is. Is the boundary function the same shit? Well, I know what linear boundary is. It's the same. Well, what is the boundary function? Is that the linear function for the linear boundary? The boundary function actually defines the log odds of the plus class in our model. Okay, so essentially in our two-dimensional example, given the point AB, this is what the log regression would do. Compute the boundary function, or the log odds function value. Let's call this T for short. Compute the odds ratio. compute the odds ratio by doing plus equals e to the t, since t is the logarithm of OR plus. Knowing odds ratio plus, it would compute p plus using this simple mathematical relation OR over 1 plus OR plus. There you go. In fact, once you know t from step 1, you can combine steps 2 and 3 to give you p plus equals et over 1 plus p t plus. RHS, what the fuck is RHS? So this is the RHS of the above equation. The right hand side? Oh, it's called a logistic function. We have now understood intuition behind the logarithm, but the question, how does it learn the boundary function? The mathematical word is beyond the scope of this, but here's a rough idea. Consider a function, g of x, where x is the data point in the training set. G of x can be defined in simple terms as if x is a part of the plus class, g of x equals p plus. Okay. Here p plus is the output given by your logistic function. If x is part of the minus class, it'd be 1 minus p plus. Oh. Intuitively, g of x quantifies probability of training purpose. Intuitively, g of x quantifies the probability that a training point was classified correctly by your model. Therefore, if you average correctly by the model, therefore if you average g of x over your entire training data, you would get the likelihood that a random data point would be classified correctly by your system. Irrespective of the class it belongs to. Simplifying things a little, it is this average of g of x that a log regression learner tries to maximize. The method adopted for the same is called the maximum likelihood. Unless you are a mathematician, you can do without learning how the optimization happens, as long as you have a good idea what is being optimized. Mostly because most systems or ML have inbuilt methods to get it done. Alright, well, this makes way more sense. But I'll be right back.